I want you to picture a scenario that I think is going to sound painfully familiar to a lot of engineers listening right now.
Oh, I think I know where this is going.
You've spent the last 6 months of your life on a project. I mean, you've designed this circuit board from the ground up.
Late nights, lots of coffee.
Exactly. You've routed thousands of traces. You've double-checked every single schematic connection. The logic, it's flawless. The code is elegant.
You're feeling good about it.
You're feeling great. So you put it on the test bench, you flip the switch, and it works. It does exactly what it is supposed to do.
The motors spin, the lights blink.
All of it. The motors spin, the LEDs blink, the data logs. It is, in your mind, a masterpiece.
It feels like a victory lap is in order at that point.
It really does. So you box it up, take it to the compliance lab for EMC testing. You're just expecting to get the rubber stamp so you can go to production.
A formality.
A total formality. You hook it up in the chamber, the antenna starts sweeping, and then you watch the red line on the spectrum analyzer just shoot straight off the charts. It fails, and not just by a little bit, it fails miserably.
That is the classic heart drop moment in engineering. It's the nightmare scenario.
It really is, and the engineer is standing there looking at this board that works perfectly in the lab, just scratching their head.
Right, because functionally, it's perfect.
Functionally, the board is a genius, but electromagnetically, it's a disaster. It's basically an accidental radio.
An accidental radio. That is the perfect way to frame it. You set out to build a motor controller or maybe a thermostat, but you inadvertently built a fairly efficient broadcast transmitter.
And that is exactly what we are digging into today. We are looking at that invisible, frustrating gap between a board that works logically, connecting point A to point B, and a board that works electromagnetically.
And it really is a huge gap.
It's massive. And it turns out a huge chunk of that difference isn't about what chips you picked or, how fast your processor is. It's about where you physically put them.
It is entirely a game of real estate. Location, location, location.
Yeah.
I mean, a slight shift in placement can mean the difference between a compliant product and a complete and very expensive redesign.
So today we are tackling board segregation, which is also known as board partitioning. We're going to unpack the art and really the science of organizing your circuit parts to keep them separate.
And, spoiler alert, this is often the secret weapon for passing those EMI tests on the first try.
It has to be.
It really is. I mean, think about it. If you master component placement, you solve the majority of your noise problems before you even route a single track.
So you're saying you can save weeks of debugging?
Weeks. Just by spending an extra day, maybe even just a few extra hours on placement.
We have a massive amount of ground to cover today. We are going to get into the nitty-gritty physics of noise, why high-speed signals are so much more, aggressive than low-speed ones.
You really are.
We're also going to bust a huge persistent myth about splitting ground planes. Seriously. If you have ever cut a ground plane to separate analog and digital, you need to listen very closely to that part.
That is a big one. A really big one.
And then we're going to look at what's called the city planning approach to board layout.
And we cannot forget cables.
Oh, right.
Because the cables are usually the things that betray you in the end. They're the final boss.
The traders of the PCB world. I love that. So before we get into the weeds, let's set the mission here. When we talk about board segregation or partitioning, what are we actually trying to achieve? What's the goal?
Well, looking at the source material we have today, we can really boil it down to three main directives. And it's not just about, making it look neat.
Right. It's not just aesthetics.
Not at all. The first goal is containment. We need to contain the high energy content of digital signals. Digital circuitry is just noisy by nature, and we need to keep that noise in a box, so to speak.
Okay, so containment is number one. Don't let the noise escape its neighborhood.
Right. Number two is avoiding what's called common impedance coupling.
That sounds like a mouthful of jargon.
It does, but it basically means we don't want different parts of the circuit sharing a confused return path where they can, shout over each other.
I always think of that like trying to have a polite conversation in a crowded bar where everyone is yelling. You can't hear anything because the background noise, the floor of the conversation is too high.
That is a very, very accurate analogy. The floor is shaking.
Okay, so containment, avoiding common impedance coupling. What's the third one?
And the third goal, and this is the big one, maybe the most important, is reducing current loop areas.
The loops.
The loops. If you can reduce the physical area of your current loops, you reduce your emissions, and simultaneously you improve your immunity to outside interference. It is a 2-for-1 deal.
Keep the loops small. I
Yeah,
feel like if we sold t-shirts, that would be on the front.
it absolutely would.
Okay, so let's get into the physics. Because to understand where to put things to minimize these loops, we first have to understand where the noise even comes from. And I think there's a common misconception that noise just equals fast clock speeds.
Right, like if I have a 100 megahertz clock, I have 100 megahertz noise.
Exactly. But it's much more nuanced than that, isn't it?
It is so much more nuanced, and this is a trap a lot of designers fall into. They look at the fundamental frequency, the clock speed, and they think that's the only enemy. But the real villain isn't the clock speed itself. It's the harmonics.
Okay, let's unpack harmonics, because I think we all learn about Fourier transforms in college. We memorize the math to pass the exam, and then we immediately flush it from our brains. So why do harmonics matter here in the real world?
It's true, Fourier is usually the first thing to go. But let's bring it back.
Yeah.
Think about a digital signal. Ideally, in your code or your timing diagram, it looks like a perfect square wave.
Right.
It goes from 0 volts to, say, 3.3 volts instantly.
Uh-huh.
Straight up, flat top, straight down.
A perfect little box.
A perfect box. But in the physical universe, nature hates sharp corners. It abhors a vacuum, and it hates sharp corners. You cannot instantly teleport voltage from 0 to 3. It takes energy and time.
So that perfect square is a lie.
It's an idealization. To create that sharp square shape, you are actually mathematically stacking up a fundamental sine wave with a whole bunch of higher frequency sine waves.
This is the Lego block idea, right? You build the square shape by stacking a bunch of round waves on top of each other.
That's a perfect analogy. You take your base frequency, your fundamental, then you add the third harmonic, then the fifth, then the seventh, and so on up into infinity.
And the more of those you add.
The more of those high frequency sine waves you stack up, the sharper the edges of your square wave become.
So if I want a signal that looks like a really crisp, perfect square, I effectively need an infinite number of high-frequency harmonics to build those corners.
Precisely. And this is where the trouble starts. This is where the EMI problem is born. The faster a signal switches, and by that I mean the faster it transitions from low to high, the more energy is pushed into those higher harmonics.
This is the rise time.
This is the rise time, or the rate of change of current over time.
If I have a signal that is kind of lazy, it ramps up slowly from 0 to 1. That's quiet.
Relatively, yes. A slow rise time means you don't need those ultra-high frequency harmonics to build the shape. The energy content drops off very quickly as frequency goes up. But modern chips aren't lazy.
Not at all.
They're incredibly fast. Even if you were running a slow clock, say, blinking an LED once a second, the edge of that blink, the transition from on to off, might happen in a nanosecond or even a picosecond.
Oh, that's a really important distinction. That's a huge gotcha.
It is.
So I could have a board that only does something once every minute, but if the chip driving it has a fast rise time, I still have a high-frequency EMI problem.
Absolutely. That rapid snap, that massive DID, creates a burst of harmonic energy that extends way, way up into the hundreds of megahertz or even gigahertz. And that energy wants to escape, wants to radiate.
So higher rate of change equals greater harmonic energy equals a higher likelihood of turning your board into that accidental radio station.
That is the correlation. And this brings us right to the impedance equation. This is absolutely foundational to all of this.
Okay.
When a signal travels down a trace, it encounters impedance.
Yeah.
Now, in DC, direct current, we just worry about resistance, good old Ohm's law.
V equals IR, the comfort zone.
The comfort zone. But we aren't dealing with DC here. We are dealing with switching signals. So the impedance isn't just resistance. It is resistance plus capacitance plus, this is the key loop inductance, or dollar.
And inductance is the one that cares about frequency.
As the frequency goes up, remember all those harmonics we just talked about? The inductive part of the impedance equation gets bigger and bigger.
So at high frequencies, the resistance of the copper trace is almost irrelevant. It's the inductance that becomes the brick wall the signal has to push against.
Exactly. The inductance dominates everything. And that changing impedance completely changes how the current behaves on the board.
I want to pause here for just a second, because this concept, moving from thinking about resistance to thinking about impedance and fields, is really the core of the mental shift a designer has to make.
It really is.
And I should mention, this deep dive is actually based on resources from the EMI design course led by Dario Fresu at Fresu Electronics.
Right, Dario Fresu. His work is fantastic.
And what I appreciate about this material is that he's not just throwing math at us for the sake of math. He's a CEO and a principal engineer. He's in the trenches. He deals with first-pass success.
That is such a crucial distinction. There is a huge difference between Understanding Maxwell's equations on a whiteboard in a university hall and actually getting a physical commercial product to pass certification in a lab so you can ship it. This material is very much about the practical application of those physics. It's about what happens on the bench in the real world.
So keeping that practical lens in mind, let's talk about the behavior of current. We have this phrase that everyone learns in Physics 101, and I hear people say it all the time. Current follows the path of least resistance.
Which is mostly a lie.
Yeah. Oh, no.
Or at least it's a dangerous oversimplification for what we do.
I feel like my entire education is crumbling. Why is it a lie?
Well, it works for DC. If you are wiring a battery to a light bulb, sure, path of least resistance, no problem. But for the signals we care about in EMI, those switching digital signals with all their high-frequency harmonics current follows the path of least impedance.
Okay, path of least impedance, not resistance. Paint a picture for me. How does that look different on a physical circuit board?
Let's visualize it. Imagine you have a signal trace on the top layer of your board. It goes from a processor to a memory chip. Underneath it, on the next layer down, you have a solid ground plane, just a big sheet of copper.
Got it.
When you send a signal out on that top trace, a return current must come back to the source to complete the circuit.
Right. If the loop isn't closed, the current doesn't flow. Basic physics.
Correct. Now, at low frequencies, let's say strictly audio range or even DC, the inductance term is tiny. It's near zero. So the impedance is dominated by resistance.
So in that case, it does follow the path of least resistance.
It does. The return current looks at that big ground plane and says, I want the shortest path with the least copper resistance. So it takes a straight line back to the source as the crow flies. It doesn't care where the signal trace above it is.
So it spreads out, it ignores where the trace is, and just cuts across the plane, taking the shortest geometric path.
Exactly. It spreads out to use as much copper as possible to lower the resistance.
Yeah.
But now let's crank up the frequency. Let's start getting into the megahertz range where those digital harmonics live.
Okay.
Now that inductive term in the impedance equation wakes up. It starts to grow and grow and grow until it dominates the equation.
And nature hates inductance, right? Nature always wants to minimize energy storage.
Nature is lazy. It wants the lowest energy state. A large physical loop creates large inductance, which stores a lot of magnetic energy. So to minimize that inductance, the return current does something fascinating.
What's that?
It stops spreading out, it condenses, and it travels directly underneath the signal trace.
It hugs the trace.
It hugs it tight. It follows the signal traces every twist and turn mirrored on the ground plane below it. Even if that means taking a longer physical path, a more meandering route, it takes that path because being close to the forward current minimizes the magnetic loop area.
That is wild. It's like a shadow.
Exactly like a shadow. And this is the whole key, because if you know that high-speed return currents are flowing directly under your traces, you can predict exactly where the noise is going to be.
But wait, this creates a problem, doesn't it? Because on a real board, we have low-frequency stuff and high-frequency stuff happening at the same time.
Yes, and that is where the trouble starts. That's where everything goes wrong. Our job as designers is to make sure those different return paths don't crash into each other. We have to minimize the interference between them.
And this is what you called common impedance coupling.
Yes. Let's try to visualize this. Imagine you have a very sensitive analog signal, maybe a temperature sensor returning to the source. It's a very low frequency, low level signal.
And on the same board, you also have a noisy digital motor driver signal returning to the source.
The librarian and the drummer.
Perfect.
Now imagine they share the same patch of copper on the ground plane. The drummer, the high current motor signal, is stomping on the floor. Because the copper has some impedance, however small, that stomping creates a voltage ripple across the ground plane.
The floor is shaking.
The floor is shaking. Now, the librarian, the sensitive analog signal, is sitting on that same shaky floor trying to read a tiny book. The librarian isn't moving, but the floor is bouncing up and down beneath it.
So from the perspective of the ADC or the processor reading the sensor.
To the processor, it looks like the sensor's value is bouncing. It's not, but its reference point, the ground is.
So your temperature reading goes crazy, not because the temperature changed, but because the ground reference changed.
Exactly. You have coupled the noise from the digital side to the analog side through the common impedance of the shared ground plane.
So the solution seems obvious, right? I think this is where most of us land intuitively.
Yeah.
If we want to stop the drummer from shaking the librarian's floor, we should just cut the floor. We take a saw, or in PCB terms, a slit in the copper, and we separate them. You have your ground, I have my ground. Problem solved.
And that is the trap. That is the dangerous myth we need to bust right now.
Hmm.
That intuitive leap is what gets so many designs into trouble.
I have to stop you there, though, because I have seen data sheets, literally application notes from major chip vendors that say separate AGND analog ground and DGND digital ground. I've seen schematics with those symbols. Are you saying those data sheets are wrong?
I am saying that in the context of modern EMC and high-frequency noise, many of them are giving advice that is dangerous for the system as a whole. Yes.
That is a bold claim. You have to walk me through this, because intuitively, cutting the plane feels like the ultimate quarantine. It's a moat. How can noise cross a moat?
It feels like a moat, but you have actually built a bridge for radiation. Think about the structure you just made. You have two large sheets of metal digital ground and analog ground, separated by a thin, non-conductive gap, a slot.
Okay, I'm with you.
Now, inevitably, you are going to have some signals or noise currents flowing. You might have a trace that has to cross that gap, which is a huge no-no we can talk about later, or you just have stray currents for the power supplies.
Right.
Because those two chunks of metal are separated, they can develop a voltage difference between them. There's no low impedance path to equalize them.
So the digital chunk might be at, say, 5 millivolts, and the analog chunk is at 0 millivolts.
Precisely. So you have two pieces of metal close to each other with a fluctuating voltage difference between them. Does that sound familiar? From physics class.
Two pieces of metal, a voltage difference.
That is the textbook definition of a dipole antenna.
Oh, wow. Okay, so by trying to stop the noise from conducting through the floor, you've actually built a structure that is perfectly designed to broadcast it through the air.
Exactly. You create a slot antenna or a dipole antenna. And the physics works both ways. Not only does it radiate your internal noise out, which is what fails you at the test lab,
It also acts as a receiver.
it makes your board incredibly susceptible to incoming noise. If a radio wave from a cell phone or a walkie-talkie hits that slot, it induces a voltage across it, which pumps noise right into your supposedly pristine ground system.
So cutting the plane is bad, we've established that.
Yeah.
But we still have the original problem. We need to separate the noisy digital stuff from the quiet analog stuff. If we can't use scissors, what do we use?
We use virtual segregation.
Virtual segregation. That sounds like something from a simulation or software?
It's actually very simple, but it requires discipline. You keep the plane solid, no cuts, one continuous, beautiful, low-impedance sheet of copper. But you discipline your component placement.
You group them. You create zones.
You partition the board, but with placement, not with copper cuts. You treat it like a map. You say this northwest corner is for digital, this middle section is for power, this southeast corner is for analog.
And because of the physics we just talked about, because high-frequency current follows the trace like a shadow, the digital return currents will naturally stay in the digital corner.
Precisely. The return current isn't going to wander over to the analog section because the path of least inductance keeps it tethered to its signal trace.
So you get the isolation you want?
You get the isolation, keeping the librarian away from the drummer, without the massive antenna risk of cutting the floor between them.
That is really elegant. You're using the laws of physics to do the work for you, rather than trying to force it with geometry cuts that have unintended consequences.
That's the goal of good EMC design.
Mm.
It's about working with the behavior of the current and the fields, not fighting against them.
So let's get practical with this layout. The source material uses this great analogy of city planning. I love this because it makes a PCB feel like a living thing, not just a static schematic.
It's a great way to visualize it. I mean, if you were building a city, you wouldn't put the noisy nightclub right next to the public library.
No.
And you wouldn't put the heavy industrial factory belching smoke next to the nursery school.
Unless you want very unhappy citizens.
Exactly. You have zoning laws. A PCB needs zoning laws.
So let's walk through the zones. We have the digital section. This is the nightclub, the noisy part of town.
This is the nightclub. High energy, flashing lights, lots of fast switching. The harmonic energy here is intense. This is where your processor, your memory, your high-speed interfaces live.
Why does it need to be so carefully isolated? Why can't I just put a digital chip next to an analog chip if I'm careful with my routing?
Because high-frequency digital signals are aggressive. They radiate effectively from the traces themselves. If you place a digital clock line physically close to a sensitive analog trace, that energy will jump across through capacitive or inductive coupling. It's called crosstalk.
So the nightclub is shaking the walls of the library next door.
Yes, but it's worse than that. It's not just about bothering the analog section.
Mm.
If that digital noise couples onto a trace that leads off the board like a power line or an analog sensor wire that goes to a cable,
Ah, the cable.
that wire becomes an antenna.
The domino effect.
Yes. The noise starts in the digital section, it hops onto a supposedly clean line, travels to the connector, and then broadcasts out through the cable. So, rule number 1 of city planning: keep the digital section deep inside the board, away from the edges and away from the sensitive stuff.
Okay, digital in the center. What about the power section? Where does that fit in our city?
The power section is like the utility plant or the heavy industry district. It handles high currents, maybe some switching regulators, which are notoriously noisy.
Right, SMPSs.
It's noisy in a different way, usually lower frequency switching noise, but higher current, which can cause ground bounce. You want this central enough to distribute power efficiently to all the other zones, but you need to keep its own return currents contained and away from sensitive analog inputs.
And the analog section, the library.
The library. The quiet residential area, this is where your sensors, your analog to digital converters, your precision amplifiers live. You want this area to be pristine.
How do you keep it pristine?
You place it such that no digital return currents ever need to cross through this territory. This goes back to the virtual segregation. If the digital section is on the left and the power is in the middle and the analog is on the right,
And your connectors are placed correctly?
then the currents flow in their own tight little loops and don't cross-contaminate. The layout effectively steers the current where you want it to go.
Now, you mentioned connectors, the exit ramps of our city, the I/O section. This seems to be where a lot of designs fall apart.
It really is.
I feel like connectors often get placed based on where they fit on the box or for user convenience rather than where they should go for physics.
Oh, absolutely. The mechanical engineer says, I want the USB port here on the front and the power port there on the back. And the electrical engineer just says, okay, without thinking about the consequences.
Right.
But in the world of EMC, cables are enemy number 1. They are the biggest threat.
Why are cables so dangerous? Why is a wire hanging off the board worse than a trace on the board?
Because a PCB is physically small. At many frequencies, say 100 megahertz, the wavelengths are long. A small board isn't a very efficient antenna for those frequencies. It's what we call electrically small. It doesn't radiate well.
Like a cable.
A cable is long. It might be a meter, 2 meters. That is a perfect quarter wave or half wave monopole or dipole antenna for a huge range of frequencies. If you put any noise onto a cable, it will radiate efficiently.
So the goal of the I/O section is to be a gatekeeper.
Exactly. It's the security checkpoint at the city border. We need to filter and shield everything right at the connector. But more importantly, the placement of the I/O section itself is critical.
The source material has a specific rule about this. Placement Rule 1. The digital section must be placed in the interior of the board, far away from the I/O edge.
Yes, this is absolutely crucial. If you run a high-speed digital trace right along the edge of the board, the electric and magnetic fields don't just stay inside the board material. They fringe out into the air.
Fringing fields, they spill over the side.
They spill over. Now imagine you have a cable connector right next to that digital trace. Those fringing fields touch the cable or the connector pins. They couple noise onto it.
So it's not even a conductive path, it's a field path.
It's a field path. It's like standing too close to a fire. You're going to get hot, even if you aren't touching the flame. You want the noisy digital stuff in the center, buffered by the ground planes, far away from the escape routes that are the cables.
That makes perfect sense. Keep the noise away from the exit. But there's another rule here that I found really interesting and maybe even a little controversial. Placement Rule 2, single side I/O. Place all your connectors on one side of the board.
Ideally, yes. This is the gold standard for EMC.
This one feels counterintuitive to me from a product design standpoint. If I have a box, I usually want plugs on the front for things I access a lot and plugs on the back for power and things that stay put. It's convenient. Why is that bad for EMI?
It's bad because of something called ground potential differences.
Okay, let's break that down. Ground potential differences.
Think about your ground plane again. We said it has impedance. Even if it's a solid sheet of copper, it's not a superconductor. It has some small amount of resistance and inductance.
Right, it's not a perfect 0-volt reference.
Not at all. Now, imagine you have noise currents flowing across the board from one side to the other. Maybe it's a processor communicating with memory or a power supply switching. That current flow creates a small voltage drop across the ground plane.
Ohm's law again. Current times impedance equals voltage. So the ground isn't perfectly flat at 0 volts everywhere. It has hills and valleys, electrically speaking.
Exactly. It's sloped. So if I have a connector on the left edge, let's say a USB port, and a connector on the right edge, maybe a power jack, the ground at the USB port might be at 0 millivolts. But the ground at the power jack might be at 5 millivolts because of all the noisy currents flowing between them.
So the two cables attached to those connectors, the USB cable shield and the power cord's ground wire, have a 5 millivolt difference between them.
Yes. And what do we call two long conductors with a voltage difference driving them?
An antenna.
A dipole antenna. You have turned your entire product, the board, plus the cables attached to it, into a giant antenna that is being driven by your internal ground noise. It will radiate at whatever frequency that noise current is.
Wow. So simply by putting connectors on opposite sides of the box, you are basically guaranteeing that any ground noise turns into radiated emissions.
You are maximizing the potential for it. But if you put all the connectors on the same side,
Then they are physically close to each other on the ground plane. They're at the same spot in the valley.
right, they are effectively at the same point on the slope. The voltage difference between their ground pins is near zero. No voltage difference means no common mode current, which means no dipole antenna driving the cables.
That is such a simple geometrical fix. It doesn't cost any money. You don't need expensive filters or shielding. You just move the connectors to one wall.
That is the beauty of good component placement. It's free. Moving a connector in the CAD software costs $0. Adding shielding cans, fair beads, or conductive foam later costs money, assembly time, and a whole lot of headache.
This ties back to what we said right at the start. It's not about what you use, it's where you put it.
It is strategy over components, every time.
Okay, so we've got our digital stuff in the middle. We've got our connectors on one edge. We aren't splitting the ground plane. What about the filtering? The source mentions a dedicated filtering section.
The filtering section should be right at the I/O edge. It's the border control. It's the last line of defense.
Why right at the edge?
Because if you put a filter on a trace, say a capacitor and an inductor, but then you run that clean trace for another 2 inches before it hits the connector, you've basically wasted the filter.
Because the trace can pick up noise again in those 2 inches.
Exactly. The noise jumps right over the filter and gets back on the line. We call it blow-by. Or the trace itself acts as an antenna, picking up internal board noise. You want the clean side of the filter to be the connector pin itself. Nothing else between them.
So layout really is this game of managing geometry and managing invisible fields.
It is. It's about visualizing the fields. We're so used to looking at schematics, which are just lines and symbols. They're an abstraction. But a PCB is a 3D physical object with electromagnetic fields swelling and pulsing around it.
And if you don't manage those fields, they manage you.
They certainly do. And they will make you fail your tests.
I want to circle back to something we touched on earlier, the idea of current loops. We said keep your loops small. Why is the loop area so critical for emissions? I get that a big loop is a big inductor, but why does it radiate more?
Think of a loop of current like a tiny magnetic coil. A loop of wire carrying a changing current generates a magnetic field. The strength of that field, and more importantly, how far it projects out into space, is directly proportional to a few things: the current, the frequency, and the area of the loop.
Like a transformer coil.
Oh.
Bigger coil, more magnetic flux.
Exactly. A large loop is a more efficient coupler to the outside world. It pushes out more magnetic energy. And conversely, it catches more magnetic energy from the outside.
So a big loop makes you a loud talker and a good listener, for noise.
In the worst possible way, yes. By keeping the return path directly underneath the signal path, by using that solid plane in correct placement, you are squashing that loop area down to almost zero. The forward and return currents are so close that their magnetic fields mostly cancel each other out. You're effectively closing the book on radiation.
So let's summarize the city plan we have built here, just to make sure we've got all the pieces.
Sure, let's do it.
We start with a solid, continuous ground plane, no cuts.
Check. No moats, no slots.
We define our zones: digital, power, analog, I/O.
Distinct neighborhoods with specific rules for who can live there.
We place the noisy digital stuff in the center for containment.
Keep the party indoors, away from the windows.
We place the sensitive analog stuff far away to prevent coupling.
Peace and quiet for the librarian.
We put all our I/O connectors on one single edge of the board.
Single side entry to minimize those ground potential differences between cables.
And we place our filters right at that edge, as close to the connectors as possible.
The security checkpoint at the border.
It sounds so manageable when you break it down like that. But I imagine in practice, when you have 1,000 components in a tiny board, it gets tricky.
It does get tricky. Competing constraints are always there. Mechanical constraints, thermal constraints. The industrial designer says the box has to be this shape. The thermal engineer says this component has to go here for airflow.
Right. Real life happens.
But that's why understanding the physics is so important. If you know why splitting the plane is bad, or why the cable placement matters so much, you can make informed trade-offs. You can negotiate.
You can push back on the mechanical engineer?
You can push back with data. You can say, okay, I can't put all connectors on one side, so I know I need to be extra careful with my ground plane impedance between them. Maybe I need more layers or a thicker ground plane there. You stop guessing and start engineering.
I love that. You aren't just connecting dots, you are managing energy fields.
It's a complete perspective shift.
It really changes the job description from PCB layout designer to something more like electromagnetic field manager.
Wow, so I'm going to put that on my business card.
You should. But seriously, this approach partitioning and placement first is the single most effective tool you have in your toolbox. You can fix a lot of things with software. You can fix some things with shielding cans and ferrets. But you can never really fix a fundamentally bad layout.
A bad layout is forever, or at least until the next board spin.
Which brings us back to the stakes we talked about at the beginning. The cost of failure.
It's huge. It's not just the $5,000 or $10,000 for the respin of the PCBs. It's the 2 months you just lost from your product schedule. It's the missed market window. It's the engineering time spent debugging instead of working on the next product. It's the company's reputation. First pass success is the holy grail.
And this guide from Freysu Electronics is really pointing the way toward that. It's about building in success from the very beginning.
It is. It's foundational knowledge.
Yeah.
If you get this right, everything else becomes easier.
I want to ask you about the domino effect again before we close. You mentioned that if a clock signal couples onto a power line, the cable becomes an antenna. Can we walk through that mechanism a bit slower? Because I think that's a gotcha for a lot of people.
Sure. It's a classic failure mode. So let's say you have a 3.3V power rail. It goes to a connector to power a remote sensor or another board. In your schematic, that 3.3V is DC. It should be a quiet, flat line.
Right. No AC component.
No AC component. But inside the board, you routed that 3.3V trace right next to a 100 megahertz clock line for the processor. And maybe you didn't have a good solid reference plane underneath them, so the fields from the clock are spreading out.
Okay, a common mistake.
A very common mistake.
Yeah.
The electromagnetic field from the changing clock signal interacts with the 3.3V trace. Through mutual inductance and capacitance between the traces, it induces a voltage on that 3.3V line.
Crosstalk.
Crosstalk. Now, your 3.3V line isn't just 3.3V DC anymore. It has a tiny 100 megahertz ripple riding on top of it.
It's carrying a passenger, a noisy one.
Exactly. That ripple travels down the trace, it hits the connector, goes out onto the wire leading to the sensor. Now, that wire, which is supposed to be carrying quiet DC power, is oscillating at 100 millihertz. It effectively becomes a broadcast antenna for your processor's clock signal.
And the compliance engineer looks at his spectrum analyzer and says, hey, I see a huge spike at 100 millihertz. And you're standing there saying, but I don't have any high-speed signals on that cable. It's just power.
And he says, well, the data says you do now.
That is terrifying.
No.
And it's completely invisible on a schematic.
Completely. It only exists in the physical layout. That is why the physical partitioning, the city planning is so key. By keeping the digital traces physically far away from the I/O traces, you dramatically reduce that coupling capacitance and mutual inductance. You physically prevent the passenger from getting on the bucks.
Distance is your friend.
Distance is the best filter. And it's free.
It's funny, we talk about high-tech solutions, complex filters, advanced simulation software, but sometimes the answer is just move it over there.
It often is. The simplest solutions are often the most robust.
So we've covered the physics, the myths, the strategy. I'm thinking about the listener right now, maybe sitting in front of their CAD tool, halfway through a layout. What should they be looking for? What's the immediate takeaway?
I would say turn off the copper pores for a second. Just look at the component place in the critical nets, the high-speed ones.
Okay.
Look at your return paths. Don't just look at where the trace goes. Imagine the current flowing back on the plane underneath. Is it a straight shot? Or does it have to snake around a bunch of vias and cuts and other components?
Imagine the ghost image on the layer below.
Yes. If you see a high-speed trace crossing over a split in the plane or crossing from your digital city into your analog suburb, stop. That's a giant red flag. Move the component. Reroute the trace. Fix the partition.
Do it now before you send the files to the fab house.
Exactly. It's so much easier to move a resistor in Altium or KCAD than it is to debug a radiating board in a multi-million-dollar anechoic chamber. Most modern professional tools allow you to define rooms or placement zones. You can literally draw boxes on your board and set rules.
What kind of rules?
You can set rules that say all components in class digital processors must stay inside this room. Or net class high-speed digital must be at least 50 mils away from net class sensitive analog.
So you can automate the discipline. You can make the tool enforce your city plan.
You can.
Yeah.
You can set up the design rules to yell at you if you violate these partitioning principles. It's like having a spelling checker for EMI.
That is incredibly useful. We rely on DRC, design rule checks, for short circuits and spacing. We should be relying on them for EMI, too.
Absolutely. The tools are there. We just have to be disciplined enough to set them up with the right intent from the beginning.
So, as we wrap up this deep dive, let's do a quick recap of the journey. We started with the concept of the accidental radio.
The device that works perfectly but broadcasts when it shouldn't.
We learned that high-frequency noise comes from the rapid rate of change-dodals and that this energy follows the path of least inductance, not resistance.
Which means it hugs the signal trace like a shadow.
We busted the myth of the split plane. Don't cut your ground. It creates dipole antennas.
It's one of the worst things you can do. Solid planes plus logic grouping equals success.
And we mapped out our city. Digital in the middle, connectors on the edge, filters at the border.
And everything in its right place, respecting its neighbors.
It's a compelling philosophy. It makes board design feel less like connecting wires and more like architecture.
It really is architecture. You are building a structure, and if the house is built well, with clear hallways and separate rooms, the electrons are happy and quiet. If the house is a mess, the electrons get rowdy and the neighbors complain.
And the neighbors in this case are the FCC or the CE certification board.
And they are very loud neighbors with very strict rules.
Indeed they are. You know, this brings me to a provocative thought to leave our listeners with. We've talked a lot about visualization today.
Yes, seeing the invisible fields.
I want you, the listener, to look at your current design. Pull it up on your screen. Now, imagine you have X-ray vision, but for current density. If you could see the return currents glowing on your ground plane right now, would they be neat, distinct lines flowing like traffic in designated lanes under their respective traces?
Or would it look like a tangled web?
A complete bowl of spaghetti with currents crossing over each other, spreading out, and crashing into barriers you've created?
That is the ultimate test.
The geometry of your placement dictates the geometry of your fields. If the glowing lines are messy, your EMI performance will be messy.
You cannot cheat physics.
You cannot cheat physics. I love that.
It's the law of the land.
Well, if this deep dive sparked your interest, if you are looking at your board right now and maybe sweating a little bit, don't worry. This is a solvable problem. You can master this.
Absolutely. It's a learnable skill, not magic.
If you want to go deeper, beyond just this conversation, you should check out the source of our insights today.
Yes, visit freezoelectronics.com. That's FRESU electronics.com.
Dario Fresu has an academy there, the Fresu Electronics Academy. You can learn directly from him. If you want to ensure your designs pass compliance the first time, that is the place to go.
It's a great resource to turn theory into real-world first-pass success.
So until next time, keep your loops small.
And your planes solid.
Thanks for listening.
Goodbye.